Welcome back to another example here. This is a continuation of example 1 where we're doing for velocity analysis. We're going to extend this for Excel. Now this is a Excel spreadsheet that we created in a previous video for where we did a full rotation of the 4-bar mechanism. And I did the original position analysis in class and have a video for doing that in class 7. In class 8, I modified it into this right here, which is for a full rotation. And I'm going to modify this for velocity. It's best to save some of these things in case you mess up. So I'm going to create a copy by right-clicking on the tab here, and I'll make a copy over here and maybe just say velocity, right? And down here, actually, I probably should have put rename this thing to not remove it, but double click on it and go FR for full rotation right here. So under the velocity one, I'm going to modify a few things. First, I want to modify this to be have a little bit of control over the amount of increments. So I'm going to go ahead and I'm going to insert a label here for what I want to do. And I'm going to hit a delta, and that's under the Greek and Coptic of these symbols. And then a theta right in here, and then equals, right? So in this cell right here, I'll make it yellow, and I'm going to make it a 5-degree increment. So whereas before I just went ahead and I dragged those as increments, I want to make some control over it because I want to change the amount of accuracy or refinement, the number of steps. It will change the accuracy or get it closer. So I'm going to hit equals the cell that's 0, the one that's right above it, and then plus 5, and then make sure I hit the F4 right here. And I'll also put little borders around it. And now I can go ahead and I double click on that little box, and that's going to make it, it's going to replace, everything's the same right here, except that it's going to be, now it's going to be based on that increment. And what I can do is I could change that increment to 1 right here, and you'll see that it counts by ones, but then over here on the graph you could see that it doesn't go for a full 60 rotation here. So I decided to go 1.25 as my increment, and then take these cells, I scroll down here, and I just grab a few of them, but you don't have to. I'm going to scroll down, and I figured out that it was down to for for a full rotation, excuse me. It's going to come down to, I think I figured out previously, it's almost for a full rotation. I think I got one more cell. Boom, 360 degrees. So I needed to go down to 304 to get 360 degrees. And but the graph over here, you noticed it only goes down to where it had it limits down to where it had 90 degrees. So what I'm going to do is on all of the graphs that I have over here, I'm going to change them because I've highlighted. If you look up at the top of this bar right here, it goes to 88, but now we said it was 304 that we wanted to go to. So let's make it 304. Boom. So that's that full rotation again. And for this guy right here, same deal, 304. And here's 304. I think in your in your homework I said to just do 5 degrees, but I wanted to show that we could do a greater refinement. So maybe this was not a necessary step here. I do it for this other curve over here too, 304. So maybe I could have saved some time by not doing that, but oh well. That's going to show you, so I just want to demonstrate the effect of the increment. Now I want to modify this to do for velocity. So I'm going to add in an omega up here at the top. That's going to be, so for symbol, I go omega, and I'll call it omega 2, and I'll subscript it. I shouldn't do this because that'll just make the video longer than it needs to be, and I don't want to waste your time. But for the problem that we're dealing with, it was 25, and that was radians per second. Okay, so I put that up there as the control. I would like to do all of this by time. So I'm going to add and insert another column right here that's going to be for time. What I should put the variable. No, the variable. It's fine to me right here. It doesn't matter. To get the time, we take the radians and divide it by the radial speed, the angular velocity, and I make sure that I make that so it's with the dollar signs. So what I can do here is I could double click that bottom corner of the cell. It'll put all those down there, and now I have something. I have time as an incremental time. And you know what? I should have made this put the little boxes around there, so that kind of makes it look neater. I also probably should have gotten rid of all my a lot of these decimal places. Maybe I'll clean that up later. What I want to do is I want to get the velocities now. So I want to get the angular velocity. I'm going to stick them, I guess I'll stick them over here. All right. So we'll be able to see the angular velocity. We put all the velocities near each other. So I'm going to cheat by taking this omega, and I'll go omega here and omega here, and I'll turn this into omega 3. And this omega 4. I'll center those to make them look pretty. And so my method of numerical differentiation is to say that equals parentheses theta 3, and I'm using, instead of just the slope of the adjacent cells, I'm going to take the cell that comes after the thing and the cell before, and then I'm going to get the slope that's like in between the two things right here. So even though I went to the second cell of here, and I could subtract out the cell before. So that's the angle before my cell, the angle after my cell and the angle before my cell. And then I want to divide by the same time increment. So I go back over to the time over here, and that one minus that one. And that will give me the slope. And I'm able to draw on top of this. So that's what that's essentially saying is I'm going to have let's see, let me draw these points. So like if I was to march off some time of something, right, and it was coming like some kind of curve that was like right here, what I've done is I've now found the slope right next to those, if that makes sense. All right, by picking the point that comes after it and the point before there, and taking that as it applies to time. And so that gives me a nice means of getting a velocity. And I could do, before I copy this down, I'll move it over to the next. I'll copy that cell over to the next one. But by shifting it over one, it has moved the bottom part, the time as well. But now I have right here. Let me fix these before I click them down and drag them. I'll put some a box around them, and I'll get rid of some of the decimal places. And now I can extend this down. I'm going to change the increment back to 5 degrees so we can kind of make a comparison what's going on right here. So here right here is theta 2, and you can see for 40 degrees right here, we could come across it. We could see what the results are. Maybe I wanted a couple more decimal places right in here. We can compare it to what we got. We got a negative 4.122 radians per second, and then but from our Excel we got negative 4.148, so that's pretty good, but maybe not great. And then for the omega 4 we got 6.998 in our hand calculations, but we get 6.945 in our computer here, our numerical simulation here. Let me change that to the well, let's see what we got. Let's go 2.5, so that's 1/2 of the increments right here, and so we could see what our 40 is going to be, right? And right here we're getting better, right? We got 4.128 compared to our 4.122. And we got 6.985 compared to our 6.998. Not too bad. Let's go a little bit more, 1.25, and let's check it out. And we can get down, so we have to scroll down some to find 40 degrees. And once again, we probably need more decimal places to really check this out. 4.123 versus our 4.122. And 6.995 compared to our 6.998. That's pretty good. That's not bad. So that's an interesting outcome. Now, what we really want for our homework is we want to get that coupler curve. Now, right here is the coupler curve, the P, the position right here. Okay, so we put that thing together. So let's take a look and see what the velocity in the of each component of those are going to be. So let's go VPX and VPY right here, and VP, right? So that we can get the velocity magnitude of those. And so we're really doing a similar thing to what we've just done. So I'm going to copy that cell over that we just did for the omega, but make sure that I bring over all the parts right here. So I take that X direction and I take this Y direction right here. Okay. And I could do the same thing over here. No, those Y's are correct, but we got to get the time. We got to fix the time right there. All right, so that's good. And then we want to get the magnitude, just because it might be interested. So we get the square root of that squared, so raise it to the caret, and plus that squared, raise it to the caret, and I think that's correct. And once again, let me get rid of some of the decimal places right here, and so I'm good to go. Right. So what I want to do, and would have been nice to have got this one thing. Okay, when I go to plot these out, by the way, we have to be careful of the very last row that we're going to have down here, right? Because remember that we were taking that slope, and we were taking the one before and after. So these guys right here are incorrect, right? They're gonna use 0. They're gonna reference a cell that doesn't have anything in it. So just be mindful of that when going to plot this right here. But I would like to plot VP versus time. No, actually, I probably, for the homework, I want VPX, right? Because I only asked for it in the X direction. Yeah, it's actually a little bit more interesting to see what's doing in the y direction as well, because this is a straight line mechanism, and what you're going to find for the angle that I asked to do is it's supposed to be completely horizontal, but we'll see there is actually a y component because it's not perfectly straight line. It's not a perfect straight line. It's actually an approximation. So, and especially that the tolerance is, you're going to be a little bit off in a bunch of different places. So you can't make a perfect straight line with the thing. That's one of the interesting parts about this problem. Let's see, how long is my video so far? It's already 15 minutes, and I don't want you to have too long of a video. But so let me plot those things out right here, and there's nothing indication for there's nothing there at 0, so I won't bother plotting that. And actually I shouldn't plot that last point, should I? Let me bring that up right there, and then come over to here, and I'm only going to plot in the x direction. I could do a lot more. This is the second time I'm making this video, and it went like way too long. So I'm purposefully I'm purposely leaving things out, because I also got the velocity at A and B, but just for a means of comparison. So I have those two columns, and I insert a graph right here. Right, and they were smart enough to get rid of the points. I always hate that it makes the graph down here at the bottom. So sometimes what I'll do is I'll go Control X. Right, this is my way of defeating this if I have a long thing, a string right here, and I'll Control V up here just to get rid of it. And let me clean up my chart a little bit. Oh, by the way, why is that going down to... I don't like that. What happened here? Why does that go down? Oh, it goes to -9 over here. What's the deal? Why does it go to -9? I got to get rid of this, not just the last row, but I got to get rid of the last 2 rows. That's why. Okay. So that's no good. Okay, so I want to make sure that we're actually plotting out this thing. It actually would be better to have, like, I should probably have made this the thing for 2 cycles would have been a better thing. So I might change the problem actually to be 2 cycles. I'm going to clean this thing up while I'm here, and I'll format things like I'll change what the numbers are here. Get rid of a decimal place. This could only need 2 decimal places for the time that's taking place. We might want to get rid of. I don't like the smoothed out feature to that. And let's make the line width a little bit less. That's a little better. Let's add some. I want to get rid of the box. I hate the box around this thing, so there's no border. Let's format. No, it's design, and add in horizontal, and add in vertical labels to this. So this is going to be I keep spelling velocity wrong. Velocity, VPX, millimeters per second, kaboom. And then have the axis title time, T, brackets, seconds. So it's always good to label what these things are right here. And let me change the increments. Now that I have this thing in here, let me change the increments back to 5 degrees right here. So that's kind of, this is actually sort of a more interesting thing to see and to plot when we go to make some comparisons. So that's actually what I asked you to do. I asked you to do it for 301 complete turn. I think I'd like you to do it for maybe 3 complete turns. So maybe I will change the instructions. I did write draft on the problem, so it doesn't really hurt you to make them more, and it will give you sort of a and I did believe I did say 5 degrees. So this is for that example, but how about I change it and modify this to be the thing that you were asked to do. So as part of the homework, I've asked you to do these dimensions right here. So I'm going to copy this over and go into my, by the way, let me double check. Has anybody come by for attendees? Nope, nobody's come by to office hours. It's always a lonely time. Let me copy this worksheet over, and I'll make this homework right here. And I think I still have this in the queue somewhere. There you go. So it's placed that in there. So now these are going to, I should change the all these things, but L1 is going to be 4, and 2 is L2, 5, and then 5, is that correct? And then AP is going to be 10 inches. Let's see if that's going to be correct. 10 inches. And the angle of this thing, all right, so the angle that we were asked to calculate as part of this, no, that's not it, don't look that. I asked you for 2 radians per second, that's important, and 120 degrees is what we ended up with right here, right? So this was 120 degrees was the angle that we're plotting out. By the way, for the Hawken thing, that's going to be 0 degrees, I believe, and then 2 was the angle right there. So I believe that's what the results should look like, but then you have to double check it here. Check out, this is good that we made this plot over here, by the way. I got to get rid of these stupid little things, these little remnants. I probably should fix my, I think it's the increment that's messed up right here. Right, so I fixed that increment to reset it right there. And that's not actually too bad. This ends up being 14 by 16. So these aren't perfectly square. They would look better if they were perfectly square. But look at that. Check it out, man. That is definitely the Hawken. And you can see that straight line right there. All right, so that's actually your homework, and that's 22 minutes into the video. You really should bring all these over into better locations that so they don't get in the way right here in your spreadsheet. Let's see. It's not really a good place to put that. A lot of times for doing these types of things, it's almost better to, I think you can put these, you could change you can move chart right here. So we can move the chart to a new sheet, right? You can make it a new sheet and go Hawken velocity. I keep spelling velocity wrong. And so you can move it to a new sheet so it doesn't get in the way. So that's often a good way to approach the thing. And then you can copy and you can paste this into your Word document. No, it's not Word. Go to a new Word document and paste it into place right here. And then you could change it around and do the things that you want with it. Oh, by the way, I probably should change what the increments of the time are going to be. A lot of times I will just make this thing, by the way, into a floater right here so I can move it around anywhere that I want. And you can write the things that you want. You could even change this to match what you usually do for the time. I usually use Times Roman for everything. I don't know why Excel has their default as being something different from the, what is it? Calibri? I don't know what the hell that is. We used to use Arial or Times Roman. That's the only two that anybody would let you use in government reports. So let's see. That was pretty good. And going back and taking a look at here, I didn't mean to make that so small. It's best to keep it like at 100%. So I usually have it at 100%. But this is a good thing to add also, except that I didn't mean to make that gray. All right, so we've actually gone as far as we need to in the in this. So anything you're listening to now is just bonus footage. I'm trying to clean this up a little bit. We don't need to make these lines that thick. Here is something, okay, we're going to modify this, but we're going to go back and fix it. Yellow isn't actually the greatest color for it, but I haven't used red, so red's a nice color as part of this. Here is an interesting thing, by the way. I'm going to change the refinement back to 1.25, by the way, 1.25, so I can get well, let's change this a couple times and we'll see what the effective is. I would like to zoom in. So that's actually the point. So we're actually in the straight line area when this thing is at 120 degrees. You'll see that the crank is at 120 degrees. We can zoom in here by modifying the increments right here. So we'll modify the increments, the axis options. Let me go, and these are all auto. So let me zoom in. That's going to be probably right around between 6 and 8 in the horizontal. So I'll go 6 and 8. We're zooming in. And now let's zoom in right here. So that's going to be between, let's say that's between 7 and 9 in the vertical direction. So I click on here, and this is not something that you have to do, by the way. This is something that I want to explore because I want to find some stuff out. This is like the usefulness of this. I want to know some things. I want to see how straight a line that straight line is. And you can already see that it's not all that straight. Let me keep zooming in. So let me make it to let's make this to 7.9 and then 8.1. How straight is that straight line? Ooh, check it out. That right there is not a straight line. It's got some dip to it. And I found that to be pretty interesting, and especially when I was using MATLAB for this, where I could really control the increments and zoom in really, really close. Actually, the increments, I'm going to have to readjust this. Is that true? No, I think I can. Let me go back and see if I can change this back to 5. Boom. And notice, you're going to notice, actually 5 wasn't actually all that bad. What happens if I do 10? My 10 increments. How bad is that going to be? Actually, that's not too bad. Do I have somebody here? In my no one showed up. All right, I thought that was a notification for office hours, but I do have an appointment. Do I have an appointment? Did I have an appointment? I totally forgot. Let's see, do I have an appointment at 10:45? No, it's 11:45. Okay, I'm good. I suddenly thought I had an appointment for something. So coming back to this right here, it's not too terribly bad, I would say. But I'll go back to my 5 increments right here, and by the way, let's see what that was. The Hawaiian velocity was 5. Let's go to 10. Let's see how bad that is. Oh, here. Oh, yeah, you can see that that's not a very good. See, you can see the edges, the faceting. So let me go back to 5. All right. So I'm just messing around with the thing. It's not necessarily anything that you necessarily have to do. as part of this. But you could actually see, oh, that's actually a pretty interesting thing, right? So my my X, I could see you could see how much it waves between. That's supposed to be the straight line part of it right there. That's pretty interesting. So we've learned, we've seen something about how the non-straight line, and it might be worth. I encourage you to go to the Norton, the chapter 3, I believe. It does a little bit of an analysis of how bad. I think that's true. It might be chapter 4. It might be chapter 4 where they go in and take a look at like how non-straight of a line an actual Hawken is. There's an example that walks it through there. Actually, I have the book right here, so let me look that up quickly for those who want to examine something a little bit more closely. It doesn't look like it's in chapter 4. So it must be chapter 3, or maybe you know what? Actually, that might be in chapter 5, where we actually go in there and because they try to make a straight line with the Hawken. Nope. Sorry. It is chapter. Yeah, it's chapter 3. It's a table 3.1 on page 144, I believe, where we're trying to optimize something for straightness. There's example 3.12, which is designing a Hawken type straight line linkage. They tell you a bunch of different things for designing it. That would actually be probably a pretty good project to work on to get to understand some of the limitations maybe of this. So let me double check chapter 5. Do we try to get the precision? Yeah, remember chapter 5 was supposed to be for synthesis. I'm getting a message from something here. So let me see. I don't see anybody. Oh, due to inactivity, your session will end in 1 minute. That's why it is telling me that. That's fine. I don't care if it kicks me out. So that's the end right there of the actual lesson. I shouldn't go any further. But I just wanted to discuss and think about the Hawken, which is this thing right here, right? So that's the Hawken 4-bar, and I could actually, let's see if I can move this thing without damaging it here. No, it doesn't want to. I don't want to break the motor here, but now I can extend it here. It'll let me. So it's kind of in that position right there, right? Anyway, we'll be analyzing that some more. Okay, so the guitar that we have today is one of my prized possessions because Eddie Van Halen sued anybody online that was trying to sell this, and then he proceeded to make a replica of the Frankenstein, the iconic Frankenstein guitar, his most famous guitar. It was actually this was actually originally a black and white guitar off of the first album, and then he started modifying it, and he put red on top of it. But this is a replica that's supposed to represent from the 1984 album, or the album 1984, the video for Jump. And at that time, he had what they call the chicken headstock on it with the Kramer logo, but there was missing a part of the Kramer logo. So this is a replica of that. And for our guitar simulation, we have it's best to have a British high gain, and I think we have some delay. Now it needs to be tuned, so this is the tuning song. Many people will hear. That's not too bad. I need more gain, man. That's got to be more gain. Didn't get that clean. It's an artificial harmonic. Now this one features a detuna, which is a mechanical engineer's kind of fascinating thing. It's this little device that pulls out and drops down. It's hard to explain, but the tuning on this, the fine tuners push down on these little rods. There's a little spring, leaf spring inside there that changes the tuning. But this little piece that you pull out is a little wedge that drops down, and it drops this string from drop detuning is a really cool thing, as opposed to detuning, down one. Van Halen guitar demonstration be without a really lousy, ham-fisted version of Eruption? That was a completely unnecessary addition to this video. But if you made it this far, congratulations. And we're done.